Right now, without any sensation or warning, you are hurtling through the cosmic void at a velocity so extreme it would tear apart any human-made structure exposed to it directly. You are riding a tiny fragment of rock, a speck that carries every story ever told, every civilization that has risen or fallen, yet in the grand scheme of the galaxy your existence does not even register. The universe around you is an endless abyss of darkness, punctuated by distant sparks of light, but each of those lights is far stranger and farther away than your intuition can truly grasp. We are about to cross mental distances that stretch the imagination until it frays, encounter structures that make our most ambitious monuments appear like dust particles, and collide with the uncomfortable understanding that every triumph, every empire, every loved one is suspended in an incomprehensible immensity that cares nothing for them. The journey begins with the idea of a single light year. Light is the fastest thing that exists. According to everything physics has established so far, nothing outruns it. This radiant courier crosses the gap from our sun to Earth in approximately 8 minutes. Yet even at that impossible speed, it needs an entire year to complete a single unit of measurement called a light year. To convert that into miles requires a number so bloated and tedious it loses meaning. Take 5.8 and tack 12 zeros onto the n5.8 trillion miles. If you climbed into a jetliner and flew non-stop at cruising speed without refueling or resting, maintaining that journey continuously, you would still need more than 6 million years to travel a single light year. Human languages were not built for such scale. Ordinary measurements collapse in the face of something this vast. Describing a distance in trillions of miles doesn't inform your brain, it simply paralyzes it. But saying 3 light years invites a different visualization. Imagine light racing through silent blackness for 3 entire years straight, never slowing before reaching its target. Even the nearest neighboring star system to the Sun lies more than 4 light years away. The photons from that star that flicker against your retina tonight began their journey when you were 4 years younger. If a catastrophic explosion consumed that system right now, Earth would remain unaware for 4 more years because distance in the cosmos also represents time. Space does not merely separate objects, it separates now from then. Every star you observe is telling you a story from the past. This isn't a metaphor. It's how the universe functions at the largest scales, and once you understand light years, you begin to see why astronomers rely on them for every significant measurement. The Milky Way is the city we live in, a sprawling metropolis of stars, and our sun orbits around its invisible centre at a distance of roughly 26,000 light years. To cross the galaxy from one edge to the other would require light, this ultimate speedster 100,000 years of uninterrupted travel. These figures should unsettle you. They should challenge the frameworks your mind has always relied upon, because what comes beyond even a light year dwarfs it into insignificance. We humans occupy a precise address within this immense spiral structure. We are not drifting randomly. Our home is located inside what astronomers call the Orion Arm, or Orion Spur, a relatively small bridge-like feature connecting 2 of the Milky Way's grander spiral arms. One, the Perseus Arm, sweeps farther from the centre. The other, the Sagittarius Arm, curves inward. We lie in a position nearer the inward boundary of this minor arm, closer to the galactic centre than to the outer rim, and though this might seem like trivia, location matters. It dictates what fills our night sky, determines the threats or protection surrounding us, and shapes what kind of environment Earth has experienced for billions of years. The distance from our Sun to the galaxy's heart has been measured using an ever-improving selection of techniques, tracking clusters of stars, observing gas clouds, calculating their movement as we circle the centre. Imagine trying to measure the boundaries of a massive forest while you stand deep among the trees. You can study the trunks, the leaves, the shadows, but determining the forest's full extent from within requires clever indirect methods. That is exactly what astronomers do with our galaxy. They map stars not by seeing the structure outright, but by calculating it. On this epic vinyl record-shaped disk of stars, we orbit halfway between the label and the outer edge. This positioning protects us from the violent chaos of the central regions, yet allows us proximity to a diverse, element-rich neighbourhood of stars and planets. Even the plane of our solar system swims through the galaxy at a steep diagonal, almost like a coin tilting as it rolls across a tabletop. And while this tilt changes our view of the star-packed band overhead, it barely alters our physical place in the vast swarm. We are right where the densest layers of starlight, dust, and gravitational influence meet, a precarious but strangely privileged position. This is the starting point for everything that follows. You may feel grounded and stationary, surrounded by familiar air and the comfortable, reassuring gravity of Earth, but the truth is far wilder. You're already part of a journey so vast, so immense, and so ancient that your ancestors could never have imagined it. And yet, here you are, riding the darkness on a silent bullet, rushing around a colossal unseen mass as your species stares upward and slowly begins to understand the scale of the abyss surrounding them. The Milky Way is not a random swirl of stars, but a meticulously structured island of matter, and we occupy a very specific niche within it, the Orion Arm, sometimes called the Orion Spur. Think of the galaxy as a glowing spiral pinwheel floating in darkness, its arms sweeping outward in immense arcs of gas, dust, and ancient light. The major arms like the Perseus arm farther from the centre, and the Sagittarius arm that curves inward, form the dominant architecture of this cosmic city. Between them stretches a smaller, narrower bridge of stars and material, and that is where our solar system resides. For decades, astronomers debated whether this structure should be classified as a minor spiral arm or merely a spur branching between larger ones. But improved observations have shown that the Orion Arm is significant enough to be considered a true component of the galaxy's grand design. Our location within this arm is not precisely at its edge and not at its centre, but slightly offset toward the inward-facing side, the region oriented toward the galactic core. That proximity plays a role in shaping the cosmic environment we experience. Too close to the centre and we'd be exposed to lethal radiation and gravitational disturbances. Too far from it, and we might drift through barren regions lacking the heavy elements needed for planets like Earth to exist. Being part of the Orion Arm grants us a visual spectacle whenever skies are dark and clear, the Milky Way band rising like a glowing river across the night. When you look up and see that luminous stripe, you're seeing along the plane of this spiral arm from within. Billions of stars layered into a compressed sliver of space all shine together, creating what appears to be a concentrated path of light. Yet what truly makes our placement uncanny is how precisely astronomers have mapped it. They have measured our distance from the galactic centre to within a margin of uncertainty that, given the scale involved, is astonishingly small, about 26,000 light-years, perhaps 27,000 depending on the method. That estimate comes from decades of tracking stellar clusters, mapping radio emissions from gas clouds, and studying how objects move under the influence of the immense mass concentrated in the core. Calculating our location inside something too large to observe from the outside is a formidable challenge, akin to trying to determine the layout of an entire metropolis while wandering only a few city blocks. But through clever analysis of motion, luminosity, and gravitational dynamics, astronomers have gradually pieced together a map of our surroundings. The Milky Way's spiral arms are not solid constructs like planetary rings. Instead, they're regions where stars appear more densely packed due to compression waves moving through the disk. As matter passes through these waves, it slows slightly in clusters, leading to bursts of star formation. Our home, the Orion Arm, is like a bustling neighbourhood situated between two major highways of swirling starlight. We are part of a suburb with just enough activity to sustain growth, but not enough chaos to threaten our long-term stability. Our solar system orbits the galactic centre in a plane that doesn't line up neatly with the galaxy's thin disk. It's tilted at nearly 60 degrees. Picture a coin flipping slowly as it moves along the rim of a spinning record. That tilt affects how the Milky Way appears to us visually, but has little impact on our overall path. We also sit slightly above the galaxy's median plane, about 55 light-years up though, in galactic proportions that offset is negligible. On a cosmic scale, we're flying almost exactly through the densest midline of the disk, embedded in a sea of stars, gas, and dust shaped into a flattened configuration by the galaxy's rotation. And that flatness is one of the most striking aspects of our existence. The Milky Way stretches about 100,000 light-years in diameter, but only around 1,000 light-years thick. Imagine a sheet of paper. Its overwhelming width compared to its height mirrors the galaxy's proportions. Billions of stars have been compressed by rotation into a disk so thin and precise that if you were to view it edge-on from a distance, it would resemble a razor blade etched across the blackness of space. This flattened structure creates more than just beauty. It shapes the physics of our region. Gravity and angular momentum keep stars swirling around the core in a synchronized sweep, while the spiral arms carve out glowing pathways of creation and decay where stars ignite brilliantly before burning out and seeding the next generation of worlds. That dynamic backdrop is the stage upon which our solar system drifts, completing a single circuit of the galaxy only once every 250 million years. The Orion Arm, with its mix of old and young stars, is a transitional region that benefits from the rich star-forming environments of both neighbouring major arms. It is neither too crowded nor too barren. It provides a distribution of elements that includes the heavy metals necessary for planetary crusts, atmospheres, life, and technology. Simply put, our home is a fortunate compromise, a location quiet enough to permit stability, bright enough to offer opportunity, and rich enough to create complexity. We owe the very existence of Earth to the particularities of this cosmic address. From here, we look outward into a night sky that is not just beautiful but meaningful. A map of where we are, a hint of how we got here, and a reminder that our neighbourhood, while minuscule in the eyes of the galaxy, is perfectly positioned to support every living thing that has ever drawn breath. Without the Orion Arm, without this unlikely perch between danger and desolation, humanity would have never existed to ask where we belong within the stars. If we could somehow step outside the Milky Way and observe it from a distance, the structure of our cosmic home would reveal itself with breathtaking clarity. Instead of the majestic spiral often shown in artistic depictions, the shape would resemble a gleaming blade, astonishingly thin when seen edge-on, stretching across space as a narrow line of concentrated starlight. The galaxy's disk is so extraordinarily flattened because rotation has squeezed billions of stars, planets, and clouds of gas into a streamlined layer. From that sideways vantage point, you would notice a swollen central bulge glowing more brightly than any other region, formed by densely packed ancient stars orbiting the supermassive black hole at the heart of the galaxy. Moving outward from that bulge, the disk gradually tapers, thinning until it fades into darkness, and remarkably, almost everything familiar to us, the sun, the planets, every constellation you have ever memorized, resides within this delicate sheet, mere hundreds of light-years thick compared to its width of 100,000 light-years. This extreme flatness influences far more than appearance. Because we live embedded inside the disk, any time we gaze toward the dense band of stars arcing across the sky, our line of sight slices through the galaxy's most populated region. Billions of distant suns stack up along that viewing angle like layers of translucent fabric, causing that glowing smear overhead. But the same geometry hides the staggering velocity at which we're all spinning through space. Without feeling the slightest breeze or vertigo, every member of the solar system is careening around the galactic centre at over 500,000 miles per hour. That number is so immense it surpasses the maximum speeds of every spacecraft humanity has ever launched by orders of magnitude. Yet because every object in our environment, the air, the ground, the oceans, the atmosphere, shares this exact motion, we remain unaware of it. Much like passengers on a plane cruising smoothly above the clouds, we sense no movement because there is no nearby reference point to reveal our furious momentum. Even though we are racing around the galaxy faster than bullets, faster than any rocket, faster than thought itself could comprehend, the distances involved are so colossal that the speed hardly seems to matter. One complete orbit of the Milky Way, often called a galactic year, takes around 225 to 250 million Earth years to complete. The last time our star occupied this same region of the galaxy, the planet was ruled by dinosaurs, and mammals cowered as insignificant creatures in the shadows of giants. Since Earth formed roughly 4.5 billion years ago, the Sun has completed only about 20 such circuits. In that time, continents have drifted apart and collided multiple times, mountains have risen and eroded away, entire biological lineages have flourished and gone extinct, and the night sky itself has been rearranged repeatedly. Yet through all of that, our star has remained locked in a gravitational dance with the invisible mass contained inside our orbit, following a path so vast it makes human history feel like a flicker of lightning in a nighttime storm. Spin faster than this, and the sun would be flung outward into the void, tearing the solar system along with it. Slow down, and gravity would drag us inward, thrusting us toward the chaotic, lethal center. We are balanced precisely within this cosmic racetrack, held in a stable lane by the forces pulling inward and the momentum pushing outward. This equilibrium is delicate, maintained by the combined gravitational influence of stars, gas, dust, and especially dark matter, the unseen substance that outweighs the visible galaxy several times over and dictates its structure and motion. Spiral arms themselves behave in unexpected ways. They are not rigid arrangements of specific stars, but more like traffic jams, density waves where matter temporarily bunches up before dispersing again. Stars drift into these patterns, slow slightly, gather, then eventually drift out again, allowing the arms to persist even as individual stars continue moving along their independent orbits. Our Sun has passed through spiral arms many times, and may do so again, each passage altering the environment around us by clustering massive short-lived stars that explode violently as supernovae, brilliant yet deadly events capable of reshaping ecosystems on planets like ours. As we carve our vast circular route through the galaxy, we do not stay fixed vertically either. Instead, the solar system oscillates above and below the galactic plane like a ship rising and falling on gentle cosmic swells, crossing through the densest region approximately every 30 million years. This subtle bobbing motion may even influence life on Earth, possibly contributing to periodic bursts of extinction or geological upheaval, though such mysteries remain under study. To make matters even more mind-bending, the disk itself is not a perfect plane. It warps and twists slightly toward its edges, bending upward on one side and downward on the other, like a spinning vinyl record that has started to ripple. That ripple, combined with gravitational nudges from nearby dwarf galaxies and immense clouds of dark matter, ensures that no part of the Milky Way remains entirely still. Everything is moving, rotating, orbiting, and vibrating, an immense choreography unfolding on scales that defy imagination. Yet through every fluctuation the Sun carries its fleet of worlds forward relentlessly. There is no stopping, no slowing down, no turning back. We are passengers strapped to a star that is following a path set over billions of years, carving a shimmering track around an unseen gravitational monarch. And though the ride feels calm and familiar, the truth is that we are participating in one of the fastest, grandest, and most astonishing journeys the universe has to offer. A journey that defines our place in the cosmos even as we remain blissfully unaware of the incredible speeds and unfathomable distances that surround us. The astonishing velocity at which we orbit the Milky Way is only one part of the solar system's monumental journey. Not only are we circling the galactic center, but the Sun itself is drifting through a dynamic gravitational landscape where densities and masses are unevenly distributed. Everything inside the galaxy contributes to this motion, from stars and dust clouds to the mysterious dark matter that forms the majority of the Milky Way's gravitational scaffolding. As the Sun races around this colossal track, its gravitational grip keeps the planets aligned, dragging Earth and the rest of the solar family with it. But if you extended your imagination outward, beyond Pluto and the Kuiper Belt, you would find icy comets in the Oort cloud, also caught up in this incredible sweep through the void. Every grain of matter bound to the Sun is participating in this ancient voyage. Even though we understand the speed mathematically, our senses remain blind to it. Motion in space does not whip your hair or tug your skin. Space provides no air, no friction, no resistance, so momentum continues unchecked. From within the solar system, everything shares the same forward rush, meaning there is nothing to indicate movement unless we compare our position to objects far beyond. Humanity only recognized this cosmic race after centuries of observing the stars carefully enough to realize they shift slightly over generations. That tiny drift revealed that the Sun and its retinue are migrating through the galaxy's disk like a lone ship crossing a vast ocean. Yet the time required for a single lap is so vast that measuring it almost feels like an act of faith. Roughly 250 million years, that is the number astronomers settled upon to define a galactic year, the period required for the Sun to complete one full orbit. Imagine the enormity of that timescale. Not a single second of human history spans even 1% of a complete lap. dinosaurs ruled the Earth during our last passage through this precise region of the galaxy. When our solar system last saw this same stretch of galactic landscape, early mammals were tiny, nocturnal survivors hiding under the feet of reptilian titans. The continents on Earth were arranged differently, clustered into strange shapes no modern human would recognize. Entire mountain ranges had not yet formed, while others that existed then have since eroded into mere stumps. The night sky would have been unrecognizable, constellations scrambled beyond interpretation, and when the sun returns here another 250 million years from now, the world will again be completely transformed. Perhaps new species will dominate the Earth, or none at all. Perhaps intelligent beings will stand under alien stars and contemplate their place, unaware of how many times their planet has circled the galaxy before their arrival. Because 250 million years is long enough to erase almost every trace of what came before and replace it with something entirely different. Yet our orbit is not perfectly consistent. Gravitational disturbances along the way, tugging from other stars, traversing spiral arms, passing near enormous clouds of molecular gas, can alter the speed slightly. Sometimes the sun moves a little faster, sometimes a little slower. Over millions of years, these small fluctuations average out, but they leave historical fingerprints that scientists attempt to decipher. One controversial hypothesis proposes that every time the solar system drifts into one of the dense spiral arms, Earth becomes more vulnerable to cosmic hazards. Massive stars, which live fast and die violently, tend to form inside these crowded environments. When they explode as supernovae, they unleash intense radiation that can sweep across nearby systems and disrupt life. Some researchers have pointed to periodic extinction events in the fossil record that might align loosely with the sun's spiral arm crossings. While not yet proven, the idea that our planet's biosphere could be shaped by the galaxy's structure adds an eerie, humbling layer to our understanding of evolution. Another striking challenge to human comprehension is the raw distance separating us from the centre of the Milky Way. We routinely state that Earth sits roughly 26,000 light-years from the core, but those are simply words until we pause to consider what they truly represent. Let's imagine you boarded a commercial aircraft, the sort used to hop continents, and pointed its nose directly toward the galactic centre. Flying at about 500 miles per hour, you would need to remain in the air continuously for 6 million years just to cover a distance that light conquers in 26,000, and even then, you'd only be travelling a tiny slice of the galaxy's full diameter. Human existence, from the earliest stone tools to today's civilizations, spans a window of time minuscule compared to what such a trip demands. Now consider light, moving at 670 million miles per hour, the universal speed limit. Even this unstoppable, tireless stream of photons requires 26 millennia to reach us from the galactic centre. That means the photons reaching your eyes tonight, from the dense stellar hub buried in the constellation Sagittarius, began their journey long before agriculture, long before cities or writing, before any recorded history. The people who first painted animals on cave walls, who hunted mammoths and survived through ice ages, those are the humans who lived when the light arriving today first set out across space. We can never see the present state of the galaxy as it truly is. We're perpetually witnessing the past, a cosmic memory delayed by distance. Every star overhead is speaking to us from another era. Some from the age when continents were fused into supercontinents, others from before humans even existed. As fast as light travels, the universe is larger still, and so, when we look outward, we are looking backward in time, always, without exception. This unavoidable delay defines astronomy, a science where observation is a form of archaeology, where telescopes are time machines granting brief glimpses into eras long gone. In this way, the Earth's position inside the galaxy becomes not just a place but a moment, fixed into the past by the speed of light itself. Right now may feel like the present, but out among the stars the universe is already far ahead of us. The concept of a galactic year is one of the most humbling ideas humans have ever encountered, because it forces us to face how brief our existence has been when measured against the galaxy's immense clock. The Sun, dragging the Earth and every fragment of our solar system along with it, takes roughly 250 million years to complete a single orbit around the Milky Way centre. 250 million years, the number flows past your eyes in an instant, yet it's a span so enormous that trying to internalise it feels like trying to swallow the ocean. The last time our world occupied this very position in its orbit, dinosaurs ruled the land, towering sauropods wandered lush plains, and massive predators stalked prey through forests utterly different from any that exist today. Flowers had barely begun evolving. No mammals larger than small rodents had yet appeared. Entire mountain ranges have risen and collapsed since then. Oceans have opened and closed. Continents that once belonged to a single superstructure have drifted into the familiar shapes modern maps show. When we try to imagine what Earth will look like the next time our solar system returns to this exact cosmic location, 250 million years into the future, the mental image collapses into speculation. Will Earth be a burning wasteland under a swollen red giant sun? Will intelligent beings of some unimaginable form inherit its surface? Will anything recognizable survive? The truth is that predicting such a distant future is far beyond humanity's reach. Yet the sheer enormity of the solar system's journey illustrates a deeper point. Everything about the galaxy operates on temporal scales, where even entire species are temporary guests. Civilizations rise, thrive, and crumble in the blink of a galactic moment. Humans observe the sky and think of stars as constant companions. But any star you admire tonight has already moved significantly since ancient astronomers first recorded positions. Every pattern in the sky is a fragile coincidence formed from stars travelling their own paths through the vast disk. The constellations we teach children and etch onto flags are shifting mosaics, temporary arrangements that will dissolve and reform into new shapes over millions of years. The heavens might seem timeless, but that illusion exists only because the changes unfold far slower than a single human lifetime. The galaxy does not pause so we can admire it. While we orbit the centre, we also drift vertically, bobbing above and below the galactic plane in a slow oscillation triggered by gravitational influences across the disk. This motion resembles a horse walking across rolling meadows, steadily moving forward while rising and falling in response to the terrain. Each vertical swing takes tens of millions of years to complete, a subtle bobbing that might expose us to denser regions of the galaxy, where cosmic hazards lurk. Some scientists have proposed that these vertical oscillations correlate with episodes of mass extinction on Earth, speculating that increased exposure to radiation or gravitational disturbances during denser phases could disrupt ecosystems. Although evidence remains inconclusive, the possibility adds weight to the idea that life on Earth is shaped not only by its environment and evolution, but by the galaxy's internal rhythms. And those rhythms extend even farther into the cosmic fabric. Astronomers have discovered that the Milky Way's disk is not perfectly flat. Instead, it gently warps. One side bends upward while the opposite side droops downward, creating a subtle saddle shape. This distortion likely stems from gravitational encounters with neighbouring dwarf galaxies, or the uneven distribution of dark matter. Whatever the cause, it reminds us that the galaxy is not a rigid system but a living structure, constantly responding to internal and external forces. Things we once imagined stable, arm structure, central alignment, rotational symmetry, turn out to be fluid and evolving over billions of years. Meanwhile, the solar system remains locked within this grand dance. We do not merely move, we are compelled to move, because gravity never allows stillness. Even our own motion includes variation. When the sun passes through one of the Milky Way's spiral arms, regions teeming with dense clouds and massive, short-lived stars, the environment becomes more dangerous. High-energy supernova explosions may erupt more frequently, cosmic radiation intensifies, and gravitational nudges from neighbouring systems can perturb comets in the Oort cloud, sending icy missiles inward toward the planets. Some researchers argue that these spiral arm crossings trigger cycles of catastrophe that reshape life on Earth. While the evidence is still debated, the idea that our planet's biological history might be influenced by galactic geography is staggering. Evolution may not proceed solely according to its own internal processes. The galaxy itself may occasionally intervene. And yet, despite all this turbulence and motion, our place in the Milky Way is fortuitously calm, a sweet spot between chaos near the centre and emptiness near the outer rim. Here, stars are spaced far enough apart to reduce the risk of stellar close encounters that could disrupt planetary orbits. There is enough heavy element enrichment, produced by previous generations of supernovae, to allow rocky planets, atmospheres, oceans, and life to form. Our orbit is nearly circular, minimizing large-scale changes in radiation exposure over time. We exist in a region where cosmic conditions have supported stability for billions of years, long enough for life to not only emerge but evolve complex intelligence capable of contemplating the galaxy that sustains it. Still, no matter how favorable our circumstances, we cannot escape the relentless clockwork of galactic scale. We are temporary residents of a cosmic system that cares nothing for our survival. The sun will continue its long, silent arc around the galaxy, whether humanity thrives, perishes, or transforms into something unrecognizable. When we speak of the now in cosmic terms, we speak of a fleeting instant. More time has passed since dinosaurs lived than will pass, before almost everything humans have created is erased. Compared to the galaxy's patience, even mountains are as fragile as sandcastles. This is what it means to live inside the Milky Way, to be part of a voyage so immense that one circuit defines the lifespan of worlds, to exist in a universe where change is constant but so slow that we mistake it for permanence, and to realize that our place is both remarkably stable and profoundly transitory. A single orbit through eternity that we will never complete. To truly grasp how extraordinary our distance from the galactic centre is, you must confront a concept that feels almost like fantasy, the unity of distance and time on a cosmic scale. When astronomers say the core of the Milky Way lies 26,000 light-years away, they are not merely stating how far it is, they are telling you how far back in history you must look to see it. A light-year is not simply a unit of distance, it is a measurement of time disguised as space. Light travels faster than anything else allowed by the laws of physics, racing through the void at 670 million miles per hour. And even at that incredible speed, it must sprint for 26,000 continuous years to close the gap between Earth and the galaxy's heart. Imagine turning your head toward the constellation Sagittarius, aiming your gaze at the cluster of stars hiding a supermassive black hole deep behind thick clouds of dust. The ancient rays of light hitting your eyes left their origin during the last ice age, when humans had not yet formed civilizations or tamed crops and animals. Those photons first began their journey when woolly mammoths still roamed, when the very idea of writing, architecture, and advanced technology was non-existent. You're looking into a time capsule, not a window. You see a version of the galaxy that no longer exists. Unimaginable changes could have taken place since then. Stars colliding, clusters forming, gas clouds swirling into new suns. But we will not witness any of those transformations until their updated light finally completes its marathon toward us. In this way, the universe enforces a strict delay on knowledge. No matter how advanced our tools become, no telescope can show us what the Milky Way looks like right now. At best, we see a mosaic of different eras. Nearby stars appear as they were recently. Farther regions show progressively older versions of themselves. Time flows differently depending on where you look. This same delay applies equally to any attempt at communication. Radio signals, though technologically impressive, travel at the same pace as light because radio is simply another form of electromagnetic radiation. If a hypothetical civilization near the galactic center used radio to call us, their message would not arrive for 26,000 years. And if humanity responded immediately, those beings would wait another 26,000 years to hear our reply. A complete conversation, a simple question and answer, would demand more than 50,000 years. To put that into perspective, 50,000 years ago, our species had only just begun dispersing widely out of Africa. Civilization was tens of thousands of years away. Human languages of that era leave us no records. Evolution itself was still sculpting the physiology and brains that would later make culture possible. By the time any reply arrived today from a message sent then, the individuals involved would be separated by so much time that they would hardly be the same species anymore. This is why science fiction loves faster-than-light messaging. Without it, coordinating anything across galactic distances becomes hilariously impractical. The laws of nature ensure that the larger the scale, the slower our awareness becomes. We live in a delayed universe, always receiving outdated information from the cosmos. Space slowly unrolls its narrative with maddening patience. And yet, despite the time lag, astronomers have devised ingenious techniques to peer through the dusty veil hiding the galactic core. The center is cloaked behind massive clouds of cosmic debris, scattered material created over billions of years as stars lived, died, and recycled their elements back into the interstellar medium. Visible light cannot penetrate that shroud, so optical telescopes see only darkness. To penetrate the obscuring clouds, we must look using different eyes, infrared detectors that sense the heat-like glow of objects beyond the dust, radio telescopes that listen to the faint whisper of hydrogen and other molecules, and instruments tuned to high-energy X-rays that can escape violent events near the black hole. With these tools, scientists reconstruct the hidden image of our galactic core, much like doctors using multiple imaging technologies to view the inside of a human body. Even so, every detail remains a glimpse into the past, a snapshot taken long before humanity understood what a galaxy was. The immensity creates another fascinating implication. Anything happening in the galaxy right now remains unknown to us, and will remain unknown for thousands or millions of years depending on the distance involved. A supernova could already be erupting at the center, unleashing more energy in a few seconds than our sun emits over its entire lifetime. And we would not know. A black hole could be consuming a massive gas cloud, shredding it into incandescent ribbons, and we would not know. New stars might be igniting in bright clusters, civilizations could be rising and falling around distant suns, catastrophic collisions might be reshaping star systems, and we would not know. The present is hidden behind a curtain of distance, and distance is synonymous with time. When we gaze outward, we gaze backward, always. Reality stretches outward like a timeline frozen from our perspective, each glowing point telling us a story that finished long before our own began. Astronomy is thus a science of ghosts. We do not observe the universe as it is, but as it was. We interpret remnants, decoding ancient signals that have wandered through the universe for unimaginable spans before touching our instruments. Everything we know is built upon echoes and delays. When you look up at the night sky, you're not witnessing a living present but a silent archive of cosmic memory. Some stars are already dead, others are newborn but invisible to us. The universe we think we see is already gone, but those ancient photons keep coming, and as long as they do, we will continue to explore the history of a galaxy that refuses to show us its true current form. Communication across galactic distances becomes almost absurd when you confront the inescapable speed limit that light, and therefore all information must obey. We are accustomed to instant connectivity on Earth. Messages travel across continents in milliseconds, we video chat with people on the opposite side of the planet in real time, and we assume that if something exists somewhere, we should be able to interact with it immediately. But that assumption collapses as soon as you step beyond the confines of our tiny world. The moment you scale communication up to the level of the Milky Way, delay becomes the defining feature, not the exception. Even if intelligent life existed near the galactic center and had already pointed sophisticated instruments in our direction, recognizing the faint radio leakage from Earth's early broadcasts, they would be detecting a version of our planet frozen in the 1990s, humans just beginning to digitize their world. And if they chose to reply right now, eagerly transmitting a message back toward this newly detected civilization, their signal would arrive to a far future Earth filled with descendants who no longer resemble us culturally, technologically, or perhaps even biologically. It would be a reply to a species that no longer exists. A simple exchange becomes a story written across millennia. Imagine attempting a conversation where each sentence must wait 26,000 years before it reaches its recipient, and another 26,000 before the response returns. A student asking a question would be long extinct before an answer arrived. Entire civilizations would rise and collapse in the silence between messages. Languages would transform beyond recognition, if they still existed at all, and evolution, working quietly in the background, might render the original communicators incapable of even understanding the reply. The concept of a dialogue loses meaning when each turn of speech spans epochs. This limitation is not technological. It is woven into the fabric of space-time. The universe has a strict rule: no signal, no matter how powerful, can outrun light. Science fiction often imagines loopholes, hyperspace, subspace frequencies, wormholes, telepathic quantum networks. But in the physical reality we inhabit, information cannot travel faster than light, and this single truth defines what is possible for interstellar communication. Even within our own galaxy, which is only one island among hundreds of billions, Any kind of coordinated activity across great distances becomes impossible. If humanity colonized worlds scattered through the Milky Way, those societies would drift apart not merely socially or politically, but temporally. A call for help or a declaration of unity would take tens of thousands of years to arrive. Remote outposts would have to develop independently, severed from any centralized authority. Empires cannot span light-year scales. They dissolve under the crushing weight of communication lag. In many ways, the universe enforces decentralization. Now consider what this means for the search for extraterrestrial intelligence. We may not only be separated from alien civilizations by distance, but by time. Their signals may arrive long after their culture has vanished, or long before they evolve the ability to interpret our response. The cosmos may be filled with civilizations shouting greetings that no one will hear until their voices become irrelevant. And even if two intelligent species existed concurrently, both equipped with the means to detect one another, the delay between message and reply would render diplomacy or cooperation functionally impossible. Interstellar war, another common science fiction trope, becomes nonsensical. There is no such thing as rapid strategy across thousands of light years. By the time an attack order reaches troops on the other side of the galaxy, the conflict's causes and combatants would have transformed beyond recognition. Communication delay is the great silencer of the stars. This distance-induced isolation also influences how we explore the universe. Astronomers do not observe objects as they truly are, but rather as they were when their light first set out toward us. We must reconstruct the present based on outdated information. Studying the galaxy becomes an act of detective work, piecing together motion, energy, and gravitational trends to predict what our instruments cannot yet see. We attempt to forecast where stars have migrated, how spiral arms have shifted, what supernovae have erupted in the centuries since their last photons arrived. The Milky Way is not a static picture. It is a dynamic process unfolding on timescales so vast that nothing we observe is current. Our maps are built from ghosts. Even more startling is the realization that remote regions of the galaxy cannot yet know that humanity exists. When our first radio broadcasts began unintentionally leaking into space around a century ago, they formed an expanding bubble of electromagnetic noise. Today, that bubble is only 100 light-years wide, a microscopic ripple in a galaxy 100,000 light-years across. Every star outside that tiny sphere of influence has no knowledge of Earth's technological rise. The overwhelming majority of the universe remains unaware that our species has learned how to communicate. We are a whisper lost in a cathedral the size of 1,000,000 worlds. And yet, despite this silence, we send signals anyway. Probing, listening, hoping. Because even if the response comes long after our civilization has vanished, the act of reaching outward is itself a declaration that we once existed and once wondered if we were alone. Communication in the galaxy is not a conversation, it is a legacy. Every message we broadcast is a message addressed to the future. The cosmos will not speak back quickly. It may never speak back at all. But humanity continues to reach across the abyss, understanding that though distance separates us, curiosity unites any minds bright enough to question the night. The galactic centre, though celebrated in photographs with its radiant clusters and luminous clouds, is not visible to human eyes in the traditional sense. When we look toward its direction in the night sky, our view is blocked by vast curtains of interstellar dust and densely packed gas woven throughout the plane of the Milky Way. These dark clouds act like heavy cosmic fog, absorbing and scattering visible light so thoroughly that no optical telescope on Earth can reveal what lies behind them. If our only window into the universe were the same narrow slice of the electromagnetic spectrum that our eyes can detect, the heart of our galaxy would remain forever hidden, a mystery buried behind an impenetrable veil. But the universe reveals itself differently when observed with the right tools. By studying wavelengths beyond visible light, infrared, radio waves, X-rays, gamma rays, astronomers peel away the obscuring dust and uncover a realm far more violent and chaotic than anything near our peaceful corner of the galaxy. Infrared cameras detect the warm glow of stars packed tightly together in the dense central regions, their collective gravity swirling gas into complex structures. Radio telescopes map gigantic molecular clouds and energetic filaments that stretch like twisted lightning through space. High-energy X-ray instruments expose searing hot matter as it falls into the supermassive black hole, its last desperate moments transformed into lethal radiation. Through this multi-wavelength vision, the centre of the Milky Way emerges not as a tranquil starry landscape, but as a roaring hub of gravitational drama. There, stars whip around the black hole at astonishing speeds, some moving thousands of kilometres per second. Orbiting so closely to an object millions of times the mass of the Sun forces them into ellipses so tight that every year counts as a single loop. Gas clouds drift too near and are ripped apart by tides, their atoms stretched and heated until they glow brighter than entire clusters of ordinary stars. Explosions from supernovae rattle the core regularly, filling it with lethal cosmic radiation. This is a neighbourhood where stars are born aggressively, live short and furious lives, then die in cataclysms powerful enough to reshape space around them. Far from the serene beauty we enjoy on Earth's night side, the centre of our galaxy is more like a cosmic foundry, a place where matter is melted down and reforged under unimaginable pressures. If the Earth somehow found itself transported near this region, life would not stand a chance. The energy pouring from the core would sterilize every surface exposed to the sky. The gravitational chaos would disrupt the delicate balance that keeps planets on stable orbits. Even if civilization had built shields, bunkers, or domed cities, the sheer amount of destructive radiation would doom the biosphere. Ironically, the dust that blocks our view also saves us. That dark material protects the outer galaxy, absorbing harmful rays and scattering the worst radiation so that only faint echoes reach our distant system. The same clouds that frustrate astronomers are the ones shielding Earth from annihilation. Living near the centre would be like taking shelter inside a lightning storm made of exploding stars. The environment is so extreme that astronomers classify it among the least hospitable zones in the Milky Way for life to evolve or persist. And yet, paradoxically, this very furnace of destruction is also a cradle for creation. Heavy elements, carbon, oxygen, silicon, iron, are forged in the cores of massive stars and released violently when they explode. Without those explosions, planets like Earth would have no solid ground, no atmosphere, no water, no biological molecules. Life as we know it is literally assembled from stellar wreckage, so while the centre would kill us instantly, it indirectly gave us everything we are. Earth exists precisely because we do not live near the source of the galaxy's most dramatic events. We are far enough away to enjoy the benefits, enriched elements, stable gravitational conditions, without suffering the consequences. Our cosmic home is therefore a compromise, close enough to the action for planet-building chemistry, distant enough to avoid obliteration. The view from Earth reminds us constantly of this strange duality. We look toward the Milky Way's bright band and see beauty, soft, milky light painted across the sky. But that glow is also a warning. Behind it lies an engine of relentless cosmic evolution. Everything in that direction is more ancient, more crowded, more dangerous than the region we inhabit. The farther one peers inward, the more intense the universe becomes. We are insulated by distance, protected by obscurity, and fortunate enough to reside in a stellar suburb where stars respect each other's space, and where life had time to evolve slowly. Still, we are irresistibly drawn to that hidden core, compelled by curiosity to uncover what lies beneath the dust. We build instruments that see beyond our eyes' limitations, not because the universe invites us, but because we refuse to accept boundaries. The galactic centre does not care whether we understand it, yet we persist, studying its secrets one wavelength at a time. Darkness is no barrier for long. Every new observatory slices through another layer of obscurity, revealing more turbulence, more grandeur, more danger. And while humans may never travel physically into that heart of fire and gravity, our understanding continues to tunnel closer with every discovery. The dust may shield us from its fury, but it cannot forever shield its mysteries. To appreciate our place in the Milky Way, it helps to scale the galaxy down to something the mind can physically picture. Imagine reducing the entire structure of the Milky Way to the size of North America. On that map, the Sun and its tiny entourage of planets would occupy only a microscopic speck floating somewhere around the border between the United States and Canada. If you zoomed in further, shrinking every distance until the entire solar system could fit inside a small city, The Earth would be like a grain of sand on a vast playground, circling a bright lamp that represents the sun, and you, standing on that grain of sand, would be smaller than a bacterium living on a single atom of that sand. That is how small we are when compared to the galaxy. Yet the analogy still fails to convey the emptiness around us. Even within our own galactic neighbourhood, the distances between stars are so immense that they make every planet seem lonely. If our sun were a ball the size of a grapefruit, the nearest star, Proxima Centauri, would be another grapefruit more than 1,000 miles away. That 1,000-mile gap between just two grapefruits is not filled with smaller stars or fragments, but almost entirely with nothing. When we say the universe is mostly empty, it is not a poetic generalization, it is a precise description. Most of space is a vacuum so deep and pure that the entire solar system could drift through it untouched for billions of years without encountering a single obstacle. People often imagine the galaxy as a crowded city of stars packed close together, shining brightly through windows of cosmic nebulae. But the reality is far more desolate. Stars are separated by gulfs wider than anything we can reasonably picture. Even the inner regions of the galaxy, where stars cluster more densely, remain mostly void. Light travels at the fastest speed possible, and yet still requires years, centuries, thousands of years to traverse the distances between stars. This emptiness is what enables the solar system to complete its 500,000 mile-per-hour journey around the galaxy without colliding into other systems. The Milky Way is like a sprawling metropolis where every building is a mile apart, and what makes the contrast even more astonishing is that this emptiness coexists with unimaginable quantity. Astronomers estimate the Milky Way holds between 100 and 400 billion stars. Spread those across a diameter of 100,000 light-years and a thickness of 1,000 light-years, and the average density becomes low enough that if you pointed a spacecraft in any direction and accelerated as fast as possible for tens of thousands of years, the odds of smacking into a star would remain nearly zero. Yet each of those billions of stars is not simply a sun. Many host planetary systems. Our own discoveries, especially since the early 2000s, have shown that planets are not rare exceptions, but the standard consequence of star formation. Wherever stars are born, disks of dust and gas whirl around them, condensing into planets, moons, asteroids, and comets. There are likely more planets in the Milky Way than there are grains of sand on all the beaches of Earth, and among those countless worlds, many orbit at favourable distances from their host stars, zones neither too hot nor too cold for liquid water to exist. The idea that Earth could be the only planet with life becomes statistically absurd. But here, again, distance intrudes. Even if nearby star systems house thriving biospheres teeming with creatures of thought and culture, their signals might still be hundreds of years away from reaching us, or thousands, or tens of thousands. Meaningful contact across such gaps becomes nearly impossible. We are surrounded by potential neighbours who may never know we exist. Still, the human mind rebels against insignificance. We are drawn to see patterns, purpose, connection. Looking up on a clear night and seeing the Milky Way spread across the heavens triggers a feeling that is older than history, or that glowing arc, which seems almost reachable, is in fact the combined light of hundreds of billions of distant suns aligned across the galactic disk. We see brightness, not because the stars are close, but because the view is stacked so deeply with stellar populations that our eyes blend them into one continuous band. If we were located above the galactic plane instead of inside it, like someone climbing a mountain to view a landscape from above, the Milky Way would appear as a vast whirlpool of starlight suspended in darkness. Instead, we are within the whirlpool, glimpsing only the spiral arms as luminous streaks across the night. It is like staring outward from inside a glowing forest. Trees seem denser in the direction where the forest stretches deepest, but that perspective hides the full shape. Because we inhabit the disk, our most beautiful view of the galaxy is also the one that reveals the least about its true form. The Orion Arm is just a single branch among many, and yet from our vantage point its star fields dominate the sky. That narrow ribbon of brilliance is both a reminder of how much surrounds us and a reminder of what we cannot see. We are inside something too large to comprehend, positioned in a location that shows us both abundance and limitation. Our home galaxy is immense, ancient, and full of wonders, but the universe refuses to give us the luxury of seeing it all at once. We must reconstruct the Milky Way slowly from the inside out, using mathematics, indirect observation, and imagination. In doing so, we begin to understand that where we live, in a sparse neighbourhood on a dust-lined road of a vast cosmic city, shapes not only our view of the stars but our very sense of existence itself. When we talk about the population of stars in the Milky Way, we must confront numbers so large they seem abstract, at least 100 billion stars, perhaps more than 400 billion, and still counting. But those aren't simple points of light scattered randomly in space. They represent an incredible diversity of stellar types, ages, and lifespans. Our own Sun is a fairly average main sequence star, a yellow dwarf quietly burning hydrogen for billions of years. Yet most stars in the galaxy are far smaller and dimmer, particularly the ubiquitous red dwarfs. These small, cool stars are like cosmic misers, conserving their hydrogen so efficiently that they can shine for trillions of years, outliving the universe as we currently know it. If life takes root around such stars, a possibility some astronomers consider highly likely, then the vast majority of life-bearing worlds could exist around red dwarf suns, thriving in systems that remain stable for unimaginable durations compared to the temporary existence of Earth. At the other extreme are massive blue stars, luminous giants burning with dazzling brilliance. They live quickly and die young, exhausting their nuclear fuel in only a few million years, the time it takes a species to evolve from primitive life to the first multicellular organisms. These bright beacons dominate star-forming regions, shaping their environments with intense radiation and monumental stellar winds. Their deaths, supernova explosions, forge the heavy elements necessary for planets, oceans, and biology. It is a strange cosmic irony that the most dangerous stars are also the universe's most generous contributors of the materials needed for life. Between these extremes there are orange dwarfs, white stars slightly hotter and more luminous than the Sun, and ancient fading stars that once blazed brightly but are now shrinking into dense spheres of carbon and oxygen known as white dwarfs. Some stars are paired or tripled, orbiting one another in intricate dances that last billions of years. Others drift alone like solitary travellers, and almost everywhere we look, we find evidence that planets accompany stars as a natural consequence of their birth. Observations of exoplanets, worlds orbiting other suns, have transformed our view of the galaxy. We used to consider our solar system a typical arrangement, but now we realize nature experiments far more creatively. Some exoplanets skim so close to their stars that a year lasts only a few hours and their surfaces glow with molten rock. Others are gas giants circling where Earth-like planets ought to sit, and still others wander freely through interstellar space without any host star at all, cold, orphaned worlds drifting through darkness. We've uncovered super-Earths larger than our planet but smaller than Neptune, worlds with deep oceans tens or hundreds of kilometers thick, planets with iron atmospheres that rain metal droplets, and potential water-rich moons orbiting giant planets like miniature solar systems. For every strange and extreme world we have discovered, astronomers suspect there are millions more waiting. If you look up on a clear night and spot a single bright star, consider that it almost certainly has planets, perhaps a handful, perhaps dozens. And if even a small percentage of those planets orbit at safe distances, maintaining temperatures that allow liquid water to exist, then habitable environments might be the rule, not the exception. The galaxy may teem with biology. Even so, astronomers must rely on indirect techniques to find these worlds. We cannot usually see an exoplanet directly. Instead, we observe how it affects the light or motion of its star. When a planet crosses in front of its star from our perspective, the starlight dims slightly, a cosmic blink that reveals the planet's size and orbit. Or we measure the star's tiny wobble, tugged by the planet's gravity, to infer the planet's mass. These methods have already uncovered thousands of planetary systems, and new observatories promise to significantly increase that number. But despite all this progress, our knowledge is still painfully incomplete. We have explored only the stars nearest to the Sun on cosmic terms, a thin shell, a fraction of the galaxy. We are like early cartographers sketching the outline of a continent while the interior remains blank. The stars within our own spiral arm alone could support millions of habitable planets, and that is only one arm among several. When we speak of 100 to 400 billion stars, we are speaking of potential. Potential for environments where chemistry experiments with complexity, where evolution might give rise to minds capable of wonder, creativity, and fear. Yet distance is again the enemy. Even if intelligent beings thrive in thousands of stellar systems, they would remain isolated behind enormous stretches of silence. Their existence might remain forever unknown to us, and ours to them. Despite this isolation, the sheer number of stars pushes against the idea that we are a singular miracle. If one star in 100 has a suitable planet, and one of those planets in 1,000 develops life, and one of those life-bearing worlds in 1,000,000 evolves intelligent beings, the galaxy could still host hundreds or thousands of civilizations scattered like sparks in a dark field. Most will never communicate, but their potential presence changes the story of existence. The Milky Way is not just a physical place, but a stage prepared for countless possible actors. Our Sun is simply one participant in a crowded cosmic gathering, and Earth is one world among billions vying for the chance to be noticed. In the end, when we consider the population of stars and planets around us, we see a galaxy that offers both humility and hope. Humility, because we are not central, not special, not even a statistical anomaly. Hope, because a universe with so many stars suggests that consciousness could bloom again and again across the spiraling arms, each instance adding light to a cosmos too large for any single species to understand. Mapping our own galaxy sounds like a straightforward task. Humans have charted the surface of Earth, mapped the Moon, and even assembled detailed surveys of distant galaxies millions of light-years away. So how hard can it be to understand the structure of the very galaxy we live inside? The answer, unimaginably hard. The difficulty arises from the simple fact that we are embedded within the Milky Way's disk, surrounded by stars and lanes of dark dust, like a person trying to map an enormous forest while standing deep inside it on a foggy night. We cannot step outside the galaxy to take a photograph of its full spiral form. Instead, we must infer its shape through deduction, geometry, and the painstaking accumulation of small clues gathered over centuries. Early astronomers could only guess at the Milky Way's nature, seeing it as a cloudy river of light arching across the sky. As telescopes improved, we realized that Milky Glow was composed of countless unresolved stars. Eventually, through observing the distribution of star clusters, gas clouds, and variable stars known as Cepheids, which allow accurate distance measurements, scientists determined that the Sun does not occupy the center, as once believed, but resides far out in one of the spiral arms. Yet even today, our maps of the galaxy are incomplete. Great swathes of the Milky Way are blocked from sight by thick banks of interstellar dust that dim and absorb visible light. To chart the hidden interior, astronomers must switch to wavelengths that can pierce the fog. Radio telescopes detect neutral hydrogen spread across the disk, revealing long skeletal curves that form the framework of spiral arms. Infrared instruments uncover stars in regions that appear totally dark through normal telescopes. Surveys measuring stellar motion show how stars swirl around the center, offering indirect hints about where masses of stars and gas concentrate. And still the picture remains partly blurred, partly guessed. We have learned that the Milky Way has multiple spiral arms, but their exact number and arrangement remain debated. Some scientists argue for 2 major arms and several minor ones. Others propose 4 primary arms. The Orion arm, our home, might not even be a full arm at all, merely a bridge or spur connecting 2 grander branches. The galactic disk is also warped, bending up on one side and down on the other like a spinning vinyl record left in the sun too long. This warp complicates mapping further, making even simple assumptions about geometry unreliable unless corrected through careful modelling. Distances add another layer of challenge. Determining how far away objects are in 3-dimensional space requires precise measurements that only recently have become possible thanks to missions like the Gaia spacecraft, which tracks the positions and motions of over 1 billion stars with extraordinary accuracy. Gaia is revolutionizing our understanding of the Milky Way's structure, revealing streams of stars left behind by ancient mergers, defining the detailed shape of spiral arms, and exposing regions where stars move unusually due to invisible clumps of dark matter. Because yes, much of the galaxy's mass is mysterious and unseen. We know the stars and gas we can detect are insufficient to explain the speeds at which the galaxy rotates. Something massive and invisible surrounds and permeates the disk, dark matter, bending gravity and controlling the motion of everything inside. That means our maps must include not only what we can observe, but what we must infer exists from gravity's effect. Creating a map of the Milky Way is like drawing a city skyline based on the shadows it casts from a distant street lamp. We also contend with time itself as an obstacle. Light takes years, centuries, millennia to travel from distant parts of the galaxy. We are mapping an object that is already different from what we see at the moment our telescopes record its light. The Milky Way rotates, evolves, births stars in glowing nurseries, and devours smaller galaxies that stray too near. Its structure is dynamic, constantly changing. Any map we produce becomes outdated the moment it is finished. Yet despite all these difficulties, the progress is astonishing. Astronomers have constructed detailed depictions of the spiral pattern, located the central bar from which the arms radiate, traced streams of stars looping through the halo, and identified stellar nurseries where new suns ignite. We have learned that globular clusters swarm around the galaxy like bees around a hive. We have tracked debris of ancient collisions, cosmic fossils recording past encounters, and each new dataset adds clarity to a picture still emerging from the shadows. The most incredible aspect of this endeavour is that it requires imagination guided by mathematics. We cannot look directly at the Milky Way's structure, so we must assemble it indirectly, like detectives piecing together a story from scattered evidence. Humans, tiny creatures clinging to a small planet in a quiet suburb of the galaxy, are using physics and ingenuity to draw the blueprint of a system 100,000 light-years wide. We are learning the shape of the very stage upon which our entire existence plays out. The value of mapping goes beyond knowledge for its own sake. Understanding our galactic environment helps explain how stars like the Sun form, how elements spread through space, how cosmic hazards travel, and how the galaxy's past shaped the conditions that allowed life to appear on Earth. Mapping the Milky Way is also mapping our history, and perhaps predicting our future. One day, distant descendants of humanity may travel far beyond the solar system, navigating from star to star. They will need not just curiosity, but charts, accurate ones, to guide them through the spiral wilderness. We map the galaxy now not to impress ourselves, but to light a path for those who will someday venture outward into the dark, making the Milky Way not just our home, but our explored domain. At the core of the Milky Way, buried deep beneath veils of interstellar dust and surrounded by stars locked in frantic orbits, lies one of the most extraordinary objects in the known universe, Sagittarius A, the supermassive black hole that anchors our galaxy. Though it cannot be seen directly, a black hole emits no light, its presence is impossible to deny because of the astonishing gravitational influence it exerts on everything nearby. Millions of stars crowd the region around the centre, but a special group of them, known as the S-stars, orbit incredibly close to an invisible point in space. These stars whip around their unseen master at breathtaking speeds, completing their orbits in mere decades instead of thousands or millions of years as most stars do. By carefully tracking their motion, astronomers have measured the mass of the object controlling their orbits, about 4 million times the mass of our Sun, all crammed into a volume no larger than our solar system. Nothing known to physics can pack that much matter into that little space, except a black hole, a place where gravity becomes so intense that not even light can escape. Sagittarius A is unimaginably dense, a gravitational trap so deep that beyond a boundary known as the event horizon, all paths lead inward. Anything, dust, gas, planets, stars, that wanders too near is stretched, compressed, and consumed, its existence erased from the visible universe. But long before that final plunge, the doomed material becomes part of a violent process that makes the area around the black hole glow fiercely at every wavelength except visible light. As gas spirals inward, friction and compression heat it to millions of degrees, causing it to emit X-rays and radio waves detectable from Earth. With the right instruments, the core becomes a bright, chaotic beacon of activity. Astronomers have recorded flares, sudden bursts of energy emerging from the region, likely triggered when clumps of matter fall too close and are devoured. This ravenous feeding hints at a larger truth. Black holes are not merely gravitational curiosities, they are engines of galactic evolution. Sagittarius A has shaped the development of the Milky Way for billions of years. Early in the galaxy's life, when gas was more abundant and stars formed more rapidly, the central black hole may have grown far larger and more active, blasting immense jets of radiation and charged particles into space. Such outbursts influence where stars can form, how gas flows through the galaxy, and even how spiral arms develop over time. Today, Sagittarius A is relatively quiet, consuming material only sporadically. But the dormant appearance is an illusion, like a sleeping volcano that retains the power to reshape landscapes when it awakens. And evidence suggests that the black hole has erupted before. Astronomers have discovered enormous bubbles of high-energy radiation towering above and below the galactic plane, gigantic structures extending tens of thousands of light-years, known as the Fermi bubbles. These colossal formations appear to be relics of a massive outburst from Sagittarius A, millions of years ago, a moment when the black hole unleashed a storm of energy so vast that its effects are still visible today. Sagittarius A is also the best-studied supermassive black hole in the universe, because it is the closest one to Earth. Observatories around the world coordinate measurements, capturing the dance of the S-stars with exquisite precision. In 2022, the Event Horizon Telescope, a network of synchronized radio telescopes linked across Earth to create a planet-sized instrument, successfully imaged the glowing ring of hot material swirling around Sagittarius A. The result was a blurry but groundbreaking portrait, a dark circular shadow encircled by a halo of fiery plasma, exactly as predicted by Einstein's theory of general relativity. That image was humanity's first glimpse of the monster that governs our galactic home, and what makes this achievement even more profound is how small the black hole appears from Earth. Though it contains millions of suns, its event horizon would fit comfortably within Mercury's orbit. From a distance of 26,000 light-years, it subtends no larger than a donut placed on the surface of the Moon as viewed from Earth, a minuscule target requiring extraordinary ingenuity to capture. The stars near Sagittarius A not only prove the black hole's existence, but also serve as a natural laboratory to test the laws of physics under extreme conditions. When the star S2 swung around the black hole during one of its closest approaches, astronomers observed subtle distortions in its motion and the stretching of its emitted light, effects predicted by relativity, confirming Einstein's equations with stunning accuracy. The galactic center thus becomes a crucible where our understanding of nature's fundamental rules is tested. And yet, for all we have learned, countless mysteries remain. How did Sagittarius A form? Did it begin as a smaller black hole that gradually expanded by devouring stars and gas, or was it born massive during the earliest epoch of the galaxy? Why is it relatively quiet today? Will it become active again? How much influence does it exert across the Milky Way at this very moment? Black holes challenge our intuition. They are regions where matter collapses into indescribable density, where time slows dramatically, and where the known equations of physics strain under their own weight. Sagittarius A, silent and obscured, is a reminder that the center of our galaxy is anything but ordinary. It is a gravitational heart, a cosmic anchor, and a symbol of the forces that sculpt galaxies themselves. Without such a black hole, the Milky Way might not exist in its current form. It is the hidden ruler of our celestial home, powerful, mysterious, and essential to everything we see when we look up into the night. As we push closer to the monstrous gravity of Sagittarius A, the normal intuition that governs our understanding of space and time begins to fail. The environment surrounding the supermassive black hole is a laboratory of extreme physics, where nature reveals its most violent capabilities. Stars that venture too close are stretched by tidal forces so powerful they can tear a sun apart atom by atom, a process known as spaghettification, a term that sounds whimsical but describes one of the most horrifying fates possible. Material stripped from stars and gas clouds forms a swirling accretion disk, a flattened incandescent whirlpool of plasma heated to millions of degrees, rotating at nearly the speed of light. Friction within this disk generates radiation so intense that a human spacecraft would disintegrate long before reaching the event horizon. Even time itself becomes distorted. To an outside observer, anything approaching the black hole slows dramatically, crawling toward the event horizon in excruciating slow motion, never quite crossing the threshold. Yet from the perspective of the falling object, the plunge continues uninterrupted, and the moment it crosses the event horizon is utterly unremarkable, until tidal forces rip it apart. Gravity becomes a sculptor of reality, dictating what is possible and what is forbidden. Beyond the event horizon, all directions lead inward. Escape is not merely unlikely, it is physically impossible. Even light, which normally defines the limit of speed and information transfer in the universe, becomes trapped, curving endlessly into the singularity. That singularity is a point, or perhaps a region, where density becomes infinite. The known laws of physics break, and our mathematical descriptions crumble into uncertainty. Black holes are places where our theories reveal their incompleteness, hinting that a deeper understanding of gravity and quantum mechanics remains undiscovered. In their vicinity, space-time is no longer the smooth fabric we imagine, but a warped and twisted landscape shaped by mass and energy. Clocks tick slower, distances stretch. Particles behave oddly. General relativity, Einstein's greatest accomplishment, predicts these effects perfectly, yet it does not explain what happens at the heart of a black hole. Meanwhile, the danger extends far beyond the event horizon itself. The space around the black hole is filled with deathly radiation. X-rays, gamma rays, charged particles flung outward in violent bursts when magnetic fields snap and reconnect in unpredictable eruptions. Some black holes, when devouring large quantities of matter, release enormous jets of energy from their poles, beams so powerful they can travel thousands of light years, lighting up interstellar gas like cosmic blowtorches. Sagittarius A currently produces only faint flickers of such activity, but evidence suggests that in the past it unleashed jets strong enough to sculpt structures visible on galactic scales today. If the black hole were to awaken into its active phase once more, Earth would feel the consequences even from its safe perch in the outer disk. Another bizarre feature of this realm is frame dragging, an effect in which the rotation of the black hole literally drags space-time around with it like a cosmic whirlpool. Near the black hole, the very structure of reality spins, meaning that objects cannot remain still relative to the galaxy. They are forced to rotate along with the black hole's spin. This phenomenon, predicted by relativity, has been indirectly observed around smaller black holes and neutron stars, and Sagittarius A is expected to influence its surroundings in similar ways, though on a scale far greater. The closer matter falls toward the event horizon, the more pronounced these distortions become until they dominate completely. For stars orbiting near Sagittarius A, such effects subtly alter their trajectories, providing further confirmation that the invisible gravitational source behaves exactly as a supermassive black hole should. In this territory, light also bends dramatically, curving around the black hole to form gravitational lenses, cosmic mirages that can duplicate or magnify distant objects. If we could hover at a safe distance and gaze toward the center, we would see a warped panorama of stars twisted into arcs or rings by gravitational influence. This warping creates the iconic shadow captured by the Event Horizon telescope, a dark silhouette representing the region from which no light escapes, surrounded by a brilliant halo of distorted, accelerated matter. Yet the most astonishing truth is that Sagittarius A is small relative to its power. If the Sun were replaced with this black hole, its event horizon would stretch just slightly beyond Mercury's orbit. The rest of the solar system, including Earth, could continue orbiting at a safe distance, oblivious to the monstrous entity at the center. Black holes do not suck everything in indiscriminately. They behave gravitationally like any mass of equivalent size, only becoming deadly when one crosses too close. That is why Sagittarius A has not consumed the entire galaxy. Stars orbit far enough away that they remain stable. The danger lies only within a tiny fraction of the core where orbits shrink dangerously tight. Despite this relative calm, the potential for chaos is ever present. A star nudged by gravitational interactions could plunge inward unexpectedly, triggering a flare that lights up the galaxy. A passing gas cloud could drift too near, igniting a feeding frenzy that temporarily transforms the black hole into a quasar-like beacon. Long periods of quiet may end in spectacular violence. This dual nature, silent yet destructive, hidden yet influential, compact yet immensely powerful, makes the region around Sagittarius A one of the most compelling environments in astrophysics. It challenges our understanding of reality, invites us to test our best theories, and reminds us that even familiar cosmic structures contain realms beyond ordinary comprehension. When we look toward the galactic center, we are looking toward the edge of what physics can currently explain, a frontier where the universe keeps its most profound secrets locked behind a curtain of gravity. And we, driven by curiosity and ingenuity, continue to push closer, determined to understand the beating heart of our galaxy, even if doing so requires rewriting the rules of nature itself. As breathtaking as the galactic center might appear in scientific images, it is also one of the most treacherous environments anywhere in the Milky Way, a region fundamentally hostile to the existence of life. If our solar system were somehow transported closer to that inner hub, Earth would instantly become unrecognizable, stripped of safety and stability by relentless forces that reign near Sagittarius A. The dense concentration of massive stars, the violent radiation storms, and the gravitational frenzy all work together to create a zone where life would struggle to emerge and almost certainly fail to survive. The inner galaxy is packed with giant, short-lived stars that live fast and die explosively. Their life cycles are measured in mere millions of years, after which they end in destructive supernovae, detonations so fierce they bombard surrounding space with lethal cosmic rays. Any planet caught in the blast radius would see its atmosphere shredded and its surface sterilized. And in the galactic center, these explosions are not rare events. They erupt frequently, seeding the region with chaos. Interstellar gas is also thicker there, feeding rapid star formation that in turn feeds further destruction. High-energy radiation floods the environment, making it a constant battlefield of photons and particles that tear apart delicate molecules such as DNA before they even have the chance to help build something alive. The concentration of mass near the center leads to another danger. Stars are so tightly packed that close encounters between solar systems become likely. A passing star need not physically collide with another to cause disaster. Its gravity alone could distort orbital paths, fling planets out of their stable zones, or send comets screaming inward like celestial bullets. Entire planetary systems can be rearranged or destroyed simply through gravitational nudges accumulating over time. Stable orbits, the crucial ingredient for long-term biological evolution, are nearly impossible to maintain in such a crowded, volatile district. In contrast, our solar system resides in a much calmer region of the galaxy, a quiet suburb comfortably far from the noisy inner metropolis. Here, stars are spaced so widely apart that the nearest neighbour lies over 4 light-years away, an enormous buffer ensuring tranquility. We evolve in cosmic peace because chaos has been kept at bay. The galactic center, however, sits in the heart of the storm. Add to that the ruling presence of the supermassive black hole. Though Sagittarius A does not actively consume stars every day, its enormous gravity creates an environment where danger never sleeps. Stars that orbit too close can be ripped apart, unleashing bursts of radiation that propagate across space. Gas clouds that fall inward generate explosive flares brighter than millions of suns. Even during calm periods, infrared scans show flickers of energy that betray a hungry beast waiting for its next meal. And if the black hole ever reignites into an active quasar state like those seen in distant galaxies, the Milky Way would experience catastrophic fallout. Jets of radiation could blast through the disk, sterilizing enormous volumes of space and possibly ending life far from the core, potentially even reaching Earth if conditions aligned terribly. Evidence suggests that such eruptions have occurred before. The giant gamma-ray structures called Fermi bubbles stand like fossilized scars above and below the galaxy, proof that the core once expelled titanic streams of energy. Should that dormant threat awaken again, anything near the center would suffer first and worst. Yet, amidst all this violence, the galactic center remains a factory for cosmic raw materials. The frequent supernovae produce the heavy elements necessary for forming rocky planets like Earth. Carbon, oxygen, iron, the ingredients for our bodies, our air and our technology, all originate from the very processes that make the inner galaxy so dangerous. Without destructive stars exploding there and elsewhere in the cosmos, our world would never have emerged. Life owes its existence to the same violence that now threatens it. This paradox defines the relationship between living things and the cosmos. We are built from stardust forged in cataclysm, but our survival requires distance from those cataclysms. The sweet spot of habitability is narrow and precarious. Farther inward, radiation becomes fatal. Farther outward, essential elements become scarce. Earth occupies a privileged position, a fortunate orbit in a fortunate region, near enough to benefit from the galaxy's chemical riches, far enough to avoid the blast furnace at its core. Astronomers call this region the galactic habitable zone, and our solar system sits right within it. Wander inward too far and the dangers multiply rapidly. The night sky would be breathtaking if viewed from the galactic centre. Thousands upon thousands of brilliant stars blazing so close together that darkness might barely exist. But that mesmerizing beauty would mask a fatal truth. That brightness comes from stars that are too close and too active. Their light a warning flare, not a comfort. No amount of technological shielding could protect a biosphere living permanently under such a barrage. Even if intelligent beings somehow arose in that region, they would fight a constant war for survival against a universe determined to dismantle them. Perhaps this is one reason we do not expect to find many life-bearing worlds clustered near the centre. Evolution requires time, and time cannot unfold properly in a landscape where reset buttons are pushed every few million years by supernova blasts or gravitational disasters. So we observe from afar, thankful for distance, grateful for obscuring dust that blocks the worst of the radiation. The galactic centre dazzles our instruments and challenges our physics, but it is not a home. It is a crucible of destruction and rebirth, magnificent, terrifying, and utterly uninhabitable. Earth thrives only because it is far from that relentless furnace. Our existence depends on that cosmic buffer, that quiet space in a galaxy whose heart is both the source of life's building blocks and the destroyer of worlds that dare to venture too near. When we consider places where life might arise in the Milky Way, it becomes clear that not all cosmic neighbourhoods are created equal. Astrobiologists use the term galactic habitable zone to describe the region where conditions are most favourable for the emergence and long-term survival of life. This concept recognises that the galaxy contains both nurturing environments and lethal ones, and that Earth's existence depends heavily on its placement within a narrow band of safety. Too close to the centre, and planets are bombarded by intense radiation, bathed in the destructive aftermath of frequent supernovae and jostled by gravitational disruptions that destabilise planetary orbits. Too far toward the outskirts, and stars form in regions impoverished of the heavier elements needed to build rocky planets and the complex chemistry essential for biology. Earth occupies a sweet spot. Not too central, not too remote, orbiting within a spiral arm but far from the core's chaos. This fortunate position has allowed our planet to remain relatively stable for billions of years, long enough for life to originate from microscopic beginnings, diversify, survive cataclysmic changes, and eventually produce intelligence capable of contemplating its place among the stars. Our solar system sits in what astronomers call the Orion Spur, a minor branch between two major spiral arms, the Sagittarius and Perseus arms. While this small placement might seem insignificant, it places us in a relatively calm, suburban area of the galaxy, not as densely populated as a main arm, but close enough to benefit from their star-forming activity. Here, stars are spaced generously enough to minimize dangerous close encounters, and radiation levels remain low enough to allow biological evolution to proceed without constant interruption. Additionally, the Sun's orbit around the galaxy is almost perfectly circular, ensuring that we maintain a safe, consistent distance from the central black hole throughout our long galactic journey. If our orbit were more elliptical, we might periodically drift too close to the inner radiation zone, potentially triggering mass extinctions or halting the progress of life. This stable path, maintained for billions of years, reveals just how finely tuned the conditions for Earth's long-term habitability truly are. The chemical makeup of our region is also crucial. The early universe consisted almost entirely of hydrogen and helium, not elements conducive to forming planets, oceans, or living organisms. Heavier elements such as carbon, nitrogen, silicon, and iron only emerge from the nuclear furnaces of stars and the explosive remains of supernovae. Billions of years of stellar evolution enriched the galaxy, gradually building up enough of these essential atoms to form worlds like Earth. But enrichment was uneven across the Milky Way, occurring more rapidly in the inner regions and more slowly in the outskirts. Our location strikes the right balance, a place where earlier generations of stars gifted us the materials for rocky planets and biological molecules, yet where the dangers associated with that enrichment, frequent stellar explosions, have lessened over time. The solar system also benefits from being part of the local bubble, a carved-out cavity of space likely formed by ancient supernovae that exploded near our region millions of years ago. This bubble is filled with thin, hot plasma and provides a protective shield by reducing the density of interstellar gas and dust nearby. Fewer dense clouds mean fewer opportunities for gravitational interactions that might destabilize the outer reservoirs of icy debris, preventing comets from being dislodged and hurled toward the inner planets in catastrophic swarms. Even small details of our cosmic address have played a role in preventing disaster. The tilt of the galactic disk, the speed of the sun's motion, its gentle oscillation above and below the midplane, all of these factors influence how exposed the solar system becomes to hazards over millions of years. Life survived not because the universe is kind, but because our particular slice of it has been unusually stable, and yet that stability is not eternal. The galaxy continues to evolve. Over vast timescales, even Earth's comfortable position will drift. The sun slowly migrates through the Orion spur, experiencing small changes in its environment. Eventually, the solar system will pass through new regions of higher or lower stellar density. It may encounter patches where cosmic rays are stronger or where gas clouds threaten gravitational disturbances. These changes unfold so slowly that no single species will witness them fully, but evolution, ever patient, will respond. Some scientists speculate that periodic deviations in Earth's environment caused by our movement through the galaxy may correlate with extinction events, though such patterns remain debated and difficult to verify. What is clear, however, is that the galaxy influences life in ways we're only beginning to understand. The idea that biology is separate from astrophysics is outdated. Life's story cannot be told without the galaxy's backdrop. The very fact that intelligence emerged here implies that the Milky Way contains conditions conducive to such outcomes, at least in specific zones. The galactic habitable zone, while still a theory under refinement, offers a compelling framework for the search for life elsewhere. It acts as a guide, directing our telescopes and probes toward environments most like our own, where chemistry has had time to assemble complexity under gentle cosmic governance. Still, we must remain humble. Even in the most favourable regions, life might be rare due to factors we cannot yet measure: planetary magnetic fields, tectonic activity, moon formation, timing of water delivery. Earth's habitability may rely on coincidences layered upon coincidences, making us feel at once incredibly lucky and astonishingly vulnerable. Nevertheless, our placement in the galactic habitable zone has given us the luxury to ponder these mysteries. It has provided a home stable enough for consciousness to emerge and for curiosity to reach outward beyond our planet's surface. The next questions are inevitable. How many other worlds share this privilege? How many other forms of life gaze up at their own night skies? The answers remain hidden among the spiraling arms, waiting for explorers bold enough to search. To understand why the Milky Way appears the way it does, we must look closely at the two major structural components that define its disk, the thin disk and the thick disk. Though their names sound similar, their roles in galactic history and their influence on star formation are profoundly different. The thin disk is where most of the familiar cosmic scenery resides: bright young stars including the Sun, swirling lanes of dust and gas, nebulae that glow with the promise of future suns, and the spiral arms that decorate astronomy posters and postcards. This region is relatively narrow compared to its diameter, stretching only a few hundred light-years above and below the galactic plane. It is the vibrant, active zone of the galaxy, where stellar nurseries ignite constantly, and where supernovae replenish the interstellar medium with the heavy elements needed for planets like Earth. Without the thin disk, the galaxy would be a much darker and quieter place. The thick disk, on the other hand, is older, puffier, and more sparsely populated, extending 1,000 or more light-years above and below the plane. Stars in the thick disk are ancient, survivors from a time when the Milky Way was still assembling itself from the collisions and mergers of smaller protogalaxies. These stars tend to have far fewer heavy elements because they formed before supernovae had enough time to enrich the galaxy with metals. Their chemical fingerprints offer clues to the earliest chapters of the Milky Way story, revealing that the galaxy did not form in a single tranquil event, but through a chaotic process of gradual growth and violent assimilation. When smaller galaxies drifted too close, gravity tore them apart, scattering their stars into the growing structure and thickening the disk over time. Thus, the thick disk is like the attic of the Milky Way, a vault of ancient artifacts from different origins holding the records of collisions long past. Meanwhile, the thin disk, the layer we inhabit, is still under construction. Its stars move in mostly orderly circular orbits, while gas clouds follow similar paths, ensuring a steady supply of raw material for future generations of stars. The beauty of the spiral arms comes not from permanent structures, but from density waves, slow-moving ripples in the disk that compress gas as they pass through, triggering star formation in brilliant arcs. These arms behave like traffic jams on a cosmic highway. Individual cars, stars and gas clouds, pass through the jam, but the jam itself remains in place, marking regions where birth rates are highest. Because new stars are born hot and bright in these areas, the arms glow with their combined radiance, creating the iconic spiral appearance of the galaxy. Yet over time, those luminous stars burn out and drift away, ensuring the spiral arms are ever-changing mosaics of new and dying suns. This ongoing cycle contrasts sharply with the thick disk, where star formation has slowed dramatically. It is the quiet after the storm, a stable region where old stars continue their lonely orbits with little new activity. To fully appreciate the disk structure, we must also consider the subtle vertical motion of the Sun and its neighbours. As the solar system travels around the galactic centre, it oscillates up and down through the thin disk like a boat riding gentle swells. This motion carries us occasionally closer to the midplane where star density is highest, and then farther into regions with fewer stellar neighbours. Some scientists propose that these oscillations could expose Earth to varying levels of cosmic risk, such as increased comet impacts or radiation exposure, though such links remain speculative. Still, it reminds us that our orbit is more complicated than a simple circular path. It is a three-dimensional journey through a dynamic environment. The boundary between the thin and thick disks is not sharp. Rather, it is transitional, a blend of populations with different ages, chemistries, and motion patterns. By studying those stars and decoding their histories, astronomers are gradually reconstructing how the Milky Way transformed from a chaotic, young structure into the elegant spiral we see today. The interplay between thin and thick disks reflects different epochs of cosmic evolution, early violence giving way to long-term stability. Gas plays a crucial role in that transformation. In the thin disk, giant clouds of hydrogen act as star factories fueled by pressure, gravity, and energy. When a massive star detonates in a supernova, its shockwaves compress nearby gas, triggering another cycle of star birth. The disk is a perpetual recycling system. Old stars die, new stars form from their remains, and planets emerge from leftover debris. Meanwhile, dark lanes of dust, which obscure our view of the galactic plane, are not merely nuisances for telescopes. They are reservoirs of molecules in the early stages of collapse, the seeds of future solar systems. If we could zoom out and watch the disk evolve over billions of years, we would see a swirling, shimmering landscape constantly reshaped by gravity and light. The spiral arms rearrange themselves like slow-moving tides. The thick disk as old stars drift as archives of forgotten mergers. The thin disk brightens and fades as new generations emerge from old ashes. And through it all, the galaxy continues spinning majestically, guided by the invisible hand of dark matter that surrounds it like a massive gravitational cocoon. The very existence of two distinct disks shows that our galaxy carries its past and present layered together. Ancient scars woven alongside ongoing creation. Earth, orbiting quietly within the thin disk, owes its existence to that history. Without the thick disk as foundational stars and without the thin disk as persistent star formation, there would be no sun, no planets, and no observers capable of contemplating the structure that sustains us. Every glance toward the Milky Way is therefore a glimpse into a living galaxy, a system built through both turmoil and tranquility, where the remnants of yesterday support the brilliance of tomorrow. If the Milky Way consisted only of stars, planets, gas, and dust, material we can see, its behavior would be radically different from what astronomers observe. In fact, the most dominant component of the galaxy is something completely invisible, detectable only through gravity, dark matter. This mysterious substance, which does not emit, absorb, or reflect light, outweighs all visible matter combined by a huge margin. The stars, nebulae, and luminous structures we admire make up only a small fraction of the galaxy's total mass, a mere 10 to 15% at most. The rest is hidden, spread out in a massive spherical halo around the Milky Way that extends far beyond the furthest stars. Without dark matter, the galaxy simply would not hold together. When astronomers first measured how stars rotate around the galactic centre, they expected outer stars to move slower than those closer in, just as planets farther from the Sun orbit more leisurely. But the data revealed something astonishing. Stars in the outer regions whirl around the galaxy almost as fast as those nearer the core. By the rules of Newtonian gravity, such high speeds should fling the outer stars into intergalactic space, like sparks from a spinning wheel. The fact that they remain bound implies that something massive, something far more abundant than visible stars, supplies the extra gravity needed to anchor them. This hidden scaffolding is dark matter, and without it the beautiful spiral arms of the Milky Way would unravel into a shapeless cloud. Although we cannot touch or see dark matter directly, its gravitational effects shape everything we observe. Its presence guided the formation of the galaxy itself, drawing gas into dense regions where the first stars ignited more than 13 billion years ago. It dictates the orbits of stars, the clustering of galaxies, and even the large-scale structure of the universe. Yet, what dark matter actually is remains one of the greatest scientific mysteries. It may be composed of exotic particles that barely interact with normal matter, passing through planets, stars, and people without leaving a trace. Thousands of such particles may be streaming through your body every second, completely unnoticed. The realization that most of the galaxy is invisible challenges human intuition. Our senses only reveal a tiny fraction of reality. We evolved to navigate a world where mass and light appear correlated. Objects we can touch and see are heavy. Objects that are invisible seem insubstantial. Dark matter exposes the flaw in that assumption. What we can observe is not what dominates. The true architecture of the Milky Way is carved by a substance we do not yet understand, a silent presence holding the galaxy in gravitational embrace. Dark matter may also be responsible for subtle features of the Milky Way's structure. Ripples in the disk, distortions and warps, could be caused by interactions with dark matter clumps, invisible satellites that tug on stars as they pass through. The thick disk, with its elevated star motions, might be evidence of long-ago collisions with dark matter-laden dwarf galaxies. Even the spacing of spiral arms could be influenced by dark matter streaming in patterns we have yet to map. Scientists can track these effects with precision instruments and simulations, gradually revealing dark matter's fingerprints across the galaxy, but the substance itself eludes direct detection. Many experiments deep underground or in space are listening for faint signals from passing dark matter particles, hoping to catch a whisper of interaction that confirms a physical nature. So far, silence. But the universe insists dark matter exists, even if it refuses to introduce itself. What we know is based entirely on gravitational inference, memory of how stars behave and how galaxies evolve. It's like seeing branches bend in the wind without ever seeing the air that moves them. The halo of dark matter surrounding the Milky Way is immense, extending perhaps 300,000 light-years from the centre, 3 times wider than the visible galaxy. Our Sun, planets, and every star we see lie deep inside this invisible sphere. Without dark matter's grip, the galaxy would disperse over time, with its components drifting apart into emptiness. It gives the Milky Way weight, structure, and endurance. This unseen mass also plays a role in fate beyond the present. When the Milky Way eventually collides with the Andromeda Galaxy billions of years from now, dark matter halos will be the first to interact, merging gravitationally long before the visible stars follow. The merger's outcome, a single, giant galaxy, will be sculpted as much by dark matter as by stars. In every way that matters, dark matter is the dominant player in the galactic story, the hidden author behind the visible chapters. And perhaps the most humbling lesson dark matter teaches is that humanity only understands a fraction of the universe. We build telescopes and detectors, propose theories, and simulate cosmic evolution. but the majority of the Milky Way's content stands just beyond our comprehension. What we call ordinary matter, the substance that builds planets, oceans, bodies, and thoughts, is merely the minority population of the galaxy. We are the visible decoration in a universe ruled by the invisible. Dark matter is the silent majority, unseen, unfelt, yet essential. It is the reason the galaxy spins, the reason stars remain clustered, the reason the Milky Way exists as a coherent home for life. To know our galaxy fully, we must solve the enigma of dark matter, the invisible glue binding the cosmos, and one day, when technology, creativity, and persistence converge, we may finally pull back the curtain and reveal what the universe has kept hidden for so long. Just as dark matter shapes the Milky Way in ways we cannot directly perceive, another elusive and even more mysterious force governs the destiny of the universe itself: dark energy. While dark matter binds galaxies together with invisible gravity, dark energy appears to do the opposite, pushing the cosmos apart, accelerating its expansion with an inexplicable repulsive effect. The discovery of dark energy in the late 1990s shocked astronomers who had assumed that gravity should gradually slow the universe's expansion after the Big Bang. Instead, distant supernova observations revealed that galaxies were racing away faster and faster, as if some hidden engine were steadily increasing the speed of cosmic expansion. Today, scientists estimate that a staggering 70% of the universe's total content is dark energy, dwarfing even dark matter in its prevalence. That makes ordinary matter, all stars, planets, nebulae, living beings, and every atom we have ever touched, a tiny minority of existence. Our familiar world is merely a thin glaze coating a universe ruled by forces we do not comprehend. Dark energy acts uniformly everywhere, filling the cosmos like a strange pressure woven into the fabric of space-time. As space grows, more dark energy appears, fueling further expansion in a feedback loop that drives galaxies farther apart with every passing moment. The Milky Way is not exempt from this phenomenon, though we cannot feel it locally. Gravity holds our galaxy tightly enough that its stars will remain bound together despite the accelerating expansion beyond our borders. Even the future collision between the Milky Way and Andromeda, predicted to occur in about 4 billion years, will proceed unaffected by dark energy's push, because their mutual gravitational attraction is stronger at such close range. However, on scales larger than galaxy clusters, dark energy dominates completely, stretching space so relentlessly that most galaxies will eventually disappear beyond our cosmic horizon, unreachable and invisible forever. The night sky of the far future will grow emptier, with the Milky Way's descendants isolated in a darkening void. Dark energy therefore not only shapes the universe physically, it also shapes the limits of our knowledge. Every year that passes pushes more of the cosmos beyond observational reach, erasing opportunities to study distant galaxies or understand our place in a widening darkness. The mystery deepens when considering what dark energy might be. It could be a property of space itself, sometimes called vacuum energy, arising from quantum fluctuations that never vanish even in emptiness. Alternatively, it might be a dynamic field that changes over time, similar to the force that drove cosmic inflation in the universe's earliest moments. Or perhaps dark energy is merely a symptom of a misunderstanding, a signal that our theories of gravity require a profound revision. If Einstein's equations need correction at cosmological scales, then the acceleration could emerge naturally from physics we have not yet discovered. And if that is true, the nature of dark energy might be fundamentally linked to the behavior of space near black holes like Sagittarius A, where general relativity also reveals its limits. Studying one mystery could help unlock the other. The influence of dark energy grows stronger as the universe expands. In the distant future, trillions upon trillions of years from now, it may become so dominant that even gravitationally bound structures are eventually torn apart. Some models predict a scenario called the Big Rip, in which galaxies fall apart, star systems unravel, planets are stripped from their orbits, and even atoms themselves are ripped open as space-time stretches infinitely. Whether this fate awaits us remains uncertain. The true character of dark energy will determine how dramatic the end becomes. What is undeniable is that dark energy dictates the long-term evolution of the cosmos. The Milky Way's history, from birth to death, unfolds under the control of an invisible force that neither emits light nor interacts with matter in any direct way. If the galaxy's formation was guided by dark matter's gravitational pull, its ultimate isolation will be enforced by dark energy's push. Together, these two unseen influences dominate existence, while ordinary matter merely responds to their commands. This realization reshapes our philosophical perspective. For most of human history, people assumed that what they could see was all there was. The stars appeared to outline the universe's boundaries, and the Earth seemed like a central stage surrounded by celestial lights. But modern cosmology has shattered that illusion. We now understand that the Milky Way, once believed to be the entirety of the universe, is but one galaxy among hundreds of billions, and even those are only small islands floating in a cosmic sea, ruled by invisible forces. The more we learn, the more insignificant visible things become in the grand total of reality. The quest to uncover the nature of dark energy is one of the greatest scientific pursuits of this age. Astronomers build giant telescopes, launch satellites to map cosmic expansion, and design experiments capable of detecting the faintest signals from the earliest eras of the universe. Each effort brings us one step closer to answers, or reveals that the mystery is even deeper than we imagined. Dark energy, like dark matter, stands as a reminder that our understanding of the universe remains incomplete. The Milky Way spins within a framework shaped by invisible mass and expands within an ever-growing realm inflated by invisible energy. And despite all our technological achievements, we still cannot grasp what most of the universe is made of. It is humbling and thrilling to realize that we live in a cosmos full of secrets yet to be decoded, where every discovery reveals hidden layers of nature waiting to challenge the limits of our imagination. Even as we search for answers to the nature of dark matter and dark energy, the Milky Way continues to evolve, gradually reshaping itself over spans of time far beyond human perception. Galaxies are not static structures frozen in place. They are dynamic ecosystems influenced by internal processes and external interactions. Over billions of years, gravitational encounters, mergers, starbirth, and stellar death collectively sculpt the galaxy's appearance and future trajectory. The Milky Way did not form in isolation. Throughout cosmic history, it has grown by consuming smaller galaxies, a process that continues even today. Streams of stars arcing across the halo are the remnants of dwarf galaxies torn apart and absorbed. These tidal streams, stretching like ribbons through space, serve as archaeological records of past galactic feasts. One such victim, the Sagittarius dwarf spheroidal galaxy, is currently in the process of being devoured, its stars stripped and redistributed into the Milky Way's halo. Another target, the Large and Small Magellanic Clouds, are interacting with us gravitationally, funneling gas toward the Milky Way that may fuel future star formation. Our galaxy acts like a gravitational predator, slowly assimilating its neighbours, growing larger and more massive over time. Yet the Milky Way has a rival that cannot be consumed. Andromeda, our nearest spiral galaxy, is on a collision course with us. Moving closer at about 110 kilometers per second, it will eventually crash into the Milky Way about 4 to 5 billion years from now. This future event, dramatic as it sounds, will unfold over hundreds of millions of years, transforming both galaxies into one enormous elliptical or lenticular system, often called Milkdromeda in scientific models. Despite the violent imagery the word collision evokes, stars are so far apart that very few will physically strike each other. Instead, their orbits will be gravitationally scrambled. Our night sky will first fill with Andromeda's vast approaching form, then twist into chaotic patterns of scattered starlight as both galaxies merge. Gas clouds colliding will ignite bursts of rapid star formation, producing clusters of brilliant young stars in stellar nurseries triggered by the cosmic upheaval. Sagittarius A, our central supermassive black hole, may find itself drawn toward Andromeda's own central black hole. The two titanic objects will spiral inward together, radiating gravitational waves as they lose energy, eventually merging into a single, even larger black hole that will dominate the core of the newly formed galaxy. This combined structure will settle into a new gravitational equilibrium, likely a more rounded shape lacking the elegant spiral arms we presently admire. Life on Earth, if it still exists by then, will not be directly harmed by this galactic merger. The Sun and its planets could survive the reorganization, perhaps tossed into a new orbit farther from the galactic center, or flung into a remote position in the expanded halo. However, by that time, the Sun itself will be nearing the end of its main sequence life, expanding into a red giant and rendering Earth uninhabitable, regardless of the galactic transformation underway around us. Long before the merger's conclusion, humanity's fate will depend on technological evolution or migration, not celestial collisions. Galactic evolution continues afterward as well. The stars formed in the starburst period of the merger will shine brilliantly but briefly, eventually aging and dying, leaving behind white dwarfs, neutron stars, and even more black holes scattered throughout the remnant galaxy. Over trillions of years, without fresh gas to sustain star formation, the galaxy will enter a quieter, dimmer phase. Its remaining stars will cool and darken. In that far future, only long-lived red dwarfs will endure, casting faint ruddy light into the cosmic night. The Milky Way's story is often described in terms of grandeur, spirals sweeping through space, supermassive black holes anchoring cosmic creation. But on the timescale of the universe, even such magnificence is temporary. Spiral arms fade, star birth slows, bright blue giants explode and vanish. Galaxies themselves live finite lives, shaped by gravity, then subdued by entropy and expansion. Dark energy's accelerating influence will isolate the merged galaxy from others, making gravitational interactions beyond the local group impossible. In the dying ages of the universe, our once crowded cosmic neighborhood will shrink to a lonely island of ancient stars drifting through an ever-growing void. Such projections can seem bleak, a universe running down, its brilliance extinguishing. But this perspective also reveals something profound. We exist during a uniquely illuminated era. The night sky overhead, filled with vibrant stars and visible galaxies, is a temporary gift. Observers in the deep future may never know that the cosmos was once full of countless galaxies beyond their reach. They might assume their isolated stellar island is all that ever existed, just as early humans once believed the Milky Way encompassed the entire universe. In that sense, humanity occupies a privileged vantage point in cosmic history, early enough to see the universe's richness, late enough to understand its workings. The Milky Way today is full of drama, colour, and change. New stars flicker to life in nebular clouds, supernovae blaze like temporary suns, ancient clusters glide through the halo, and invisible forces choreograph the galaxy's rotation and growth. We have arrived at a moment when we can trace these processes, decode the past, and predict the future with astonishing accuracy. The galaxy is not merely a setting for life, it is a living system itself, constantly reshaped by physics, time, and chance. To understand the Milky Way is to recognize that our existence is intertwined with a much larger story, one written across billions of years, using stars as its language, and as long as curiosity drives us, we will continue deciphering that cosmic narrative, piece by invisible piece, uncovering our origins and contemplating our destiny in a universe that is endlessly changing. When we look up at the Milky Way stretching across a dark sky, we are doing more than admiring a band of faint stars. We are witnessing a cross-section of our home galaxy from the inside, a reminder that Earth belongs to a vast cosmic community. Every point of the light represents a story, stars forming, shining, aging, and ultimately contributing their elements back into the galactic environment. Our Sun is simply one chapter among billions, a recent addition in an ongoing saga that began long before humans emerged and will continue long after our species is gone. The Milky Way is more than a structure of gas, dust, and dark matter. It is a cradle for life, a library of cosmic history, and a frontier filled with unanswered questions. With each new discovery, our understanding expands, revealing newfound complexity in what once seemed ordinary. We now know that the galaxy's elegant spiral shape hides ancient collisions, that its bright disk is supported by an invisible halo, and that its long-term evolution is governed by forces no human can see, but that scientists are determined to unravel. From the bustling core ruled by the colossal gravity of Sagittarius A to the silent outskirts, where solitary stars wander, the Milky Way contains environments both nurturing and hostile, creative and destructive, chaotic and stable. Our own survival depends on the favourable conditions of a quiet orbital neighbourhood insulated from the dangers nearer the centre. A stroke of cosmic luck that made intelligent life possible here. And yet, curiosity compels us to venture beyond that comfort. We build instruments to peer into radiation-filled regions where life cannot flourish, shine telescopes through obscuring dust, and detect signals from the invisible scaffolding of dark matter. We do this because understanding the galaxy is, in a sense, understanding ourselves. The atoms in our bodies originated in stars that lived and died long before the formation of the sun. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in nuclear reactions deep inside ancient stellar furnaces. We are living testaments to the Milky Way's capacity for transformation, its ability to turn simple hydrogen into complexity, chaos into order, and dust into thinking beings. This knowledge reshapes our sense of belonging. We are not separate from the galaxy. We are one of its many outcomes. The pursuit of understanding our galactic home also drives technological and intellectual progress. Mapping the Milky Way requires ingenuity, space-based observatories capable of seeing in wavelengths the human eye cannot detect, precise measurements of star motions using instruments like Gaia, and global collaborations linking telescopes across continents to create images of black holes. As we refine our models, we reconstruct the galaxy's hidden past, track its shifting future, and learn how common or extraordinary planetary systems like our own may be. The discovery of thousands of exoplanets over the last few decades suggests that the Milky Way is teeming with worlds, some potentially Earth-like, orbiting within habitable zones around their stars. This raises an exhilarating possibility. Somewhere in the vast expanse, intelligence might have emerged independently. Other observers could be staring out at their own skies, asking the same questions we ask. Where did we come from? What else is out there? How long will our world endure? Yet if other civilizations exist, the scale of the Milky Way makes communication and meeting extraordinarily difficult. Light, the fastest carrier of information, takes more than 100,000 years to cross the galaxy's diameter, and civilizations may rise and fall within such spans. The galaxy is immense and time is long. Intelligence could be scattered sparsely, isolated by distance and the finite speed of technological reach. Even so, the search continues, because the discovery of even the faintest sign of life elsewhere would reshape our understanding of the galaxy and our place within it. The Milky Way, viewed from afar, would reveal itself as a grand spiral, glowing with the light of stars and threaded with dark paths of dust. But from here, we only glimpse a slice. To truly comprehend it, humanity must keep pushing outward, sending probes deeper into space, developing artificial intelligence to decode cosmic patterns, and eventually venturing beyond our solar system. One day, travellers may navigate by the spiral arms as ancient sailors once navigated by constellations. Human footsteps may echo on worlds that orbit distant stars within this same galaxy that created us. The Milky Way is not merely a backdrop, it is a destination. Looking ahead, the galaxy promises discoveries that will challenge our philosophies, technologies, and perceptions of reality itself. From black holes warping time to the unexplored nature of most of the cosmos, dark matter and dark energy, the Milky Way remains full of enigmas that beckon investigation. The more we learn, the more we realize how much remains hidden. But that is the essence of exploration, knowing that the unknown is larger than the known, and embracing the pursuit anyway. Standing on a small planet orbiting an ordinary star in a single spiral arm, humanity has only begun to read the first pages of a monumental story. The night sky reminds us of our origins and invites us toward our future. The Milky Way is our birthplace, our anchor, and our window into the broader universe. As we continue to unlock its secrets, we deepen our understanding not only of cosmic evolution, but of ourselves. Transient sparks of consciousness briefly illuminating a galaxy that has existed for billions of years and will continue long after we fade. And in that brief shimmer of awareness, we recognize something profound. We are the galaxy awakening to discover itself,